Carbon and its compounds, chapter 4. In the last chapter we came to know many compounds of importance to us. In this chapter we will study about some more interesting compounds and their properties. Also we shall be learning about carbon, an element which is of immense significance to us in both its elemental form and in the combined form. Activity 4.1. Make a list of 10 things you have used or consumed since the morning. Compile this list with the lists made by your classmate and then sort the items into the adjacent table. If there are items which are made up of more than one material, put them into both the relevant columns of the table. The table consists of 3 columns. First, things made of metal. Second, things made of glass or clay. And third, others. Look at the items that come in the last column of the above table filled by you. Your teacher will be able to tell you that most of them are made up of compounds of carbon. Can you think of a method to test this? What would be the product if a compound containing carbon is burned? Do you know of any test to confirm this? Food, clothes, medicines, books, or many of the things that you listed are all based on this versatile element carbon. In addition, all living structures are carbon-based. The amount of carbon present in the Earth's crust and its atmosphere is quite meager. The Earth's crust has only 0.02%. Let me repeat that. The Earth's crust has 0.02% carbon in the form of minerals like carbohydrates, hydrogen carbonates, coal and petroleum, and the atmosphere has 0.03%. The atmosphere has 0.03% of carbon dioxide. In spite of this small amount of carbon available in nature, the importance of carbon seems to be immense. In this chapter, we will know about the properties of carbon which make carbon so important to us. Topic 4.1. Bonding in carbon, the covalent bond. In the previous chapter, we have studied the properties of ionic compounds. We saw that ionic compounds have high melting point and boiling points and conduct electricity in solution or in the molten state. We also saw how the nature of bonding in ionic compounds explains these properties. Let us now study the properties of some carbon compounds. Most carbon compounds are poor conductors of electricity, as we have seen in chapter 2. From the data given in table 4.1 on the boiling and melting points of the carbon compounds, we find that these compounds have low melting and boiling point as compared. Table 4.1, melting points and boiling points of some compounds of carbon. Compound: acetic acid, melting point 290, boiling point 391. Chloroform, melting point 209, boiling point 334. Ethanol, melting point 156, boiling point 351. Methane, melting point 90, boiling point 111. We can conclude that the forces of attraction between the molecules are not very strong. Also, the melting point and boiling point are mentioned in Kelvin. Since these compounds are largely non-conductors of electricity, we can conclude that the bonding in these compounds do not give rise to any ions. In class 9th, we learned about the combining capacity of various elements and how it depends on the number of valence electrons. Let us now look at the electronic configuration of carbon. The atomic number of carbon is 6. What would be the distribution of carbons in various shells of carbon? How many valence electrons will carbon have? We know that the reactivity of elements is explained as their tendency to attain a completely filled outer shell, that is, attain noble gas configuration. Elements forming ionic compounds achieve this by either gaining or losing electrons from the outermost shell. In the case of carbon, it has 4 electrons in its outermost shell and needs to gain or lose 4 electrons to attain noble gas configuration. If it were to gain or lose electrons, first, it could gain 4 electrons forming C4 negative anion, but it would be difficult for the nucleus with 6 protons to hold on to 10 electrons, that is 4 extra electrons. Second, it could lose 4 electrons forming C4 positive cation, but it would require a large amount of energy to remove 4 electrons, leaving behind a carbon cation with 6 protons in its nucleus holding on to just 2 electrons. Carbon overcomes this problem by sharing its valence electrons with other atoms of carbon or with atoms of other elements. Not just carbon, but many other elements form molecules by sharing electrons in this manner. The shared electrons belong to the outermost shells of both the atoms and lead to both atoms attaining the noble gas configuration. But before going on to compounds of carbon, let us look at some simple molecules formed by the sharing of valence electrons. The simplest molecule formed in this manner is that of hydrogen. As you have learnt earlier, the atomic number of hydrogen is 1. Hence, hydrogen has 1 electron in its K shell, the first shell, and it requires 1 more electron to fill the K shell. So 2 hydrogen atoms share their electrons to form a molecule of hydrogen, H2. This allows each hydrogen atom to attain the electronic configuration of the nearest noble gas, helium, which has 2 electrons in its K shell. We can depict this using dots or crosses to represent valence electrons. The shared pair of electrons is said to constitute a single covalent bond between the hydrogen atoms. A single covalent bond is also represented by a line between the 2 atoms. The atomic number of chlorine is 17. What would be its electronic configuration and its valency? 287. Chlorine forms a diatomic molecule, Cl2. Can you draw the electron dot structure for this molecule? Note the only valence shell electrons need to be depicted. In the case of oxygen, we see the formation of double bond between 2 oxygen atoms. This is because an atom of oxygen has 6 electrons in its L shell. The atomic number of oxygen is 8 and it requires 2 more electrons to complete its octet. So each atom of oxygen shares 2 electrons with another atom of oxygen to give us the structure shown in figure 4.3. The 2 electrons contributed by each oxygen atom gives rise to 2 shared pairs of electrons. This is said to constitute a double bond between the 2 atoms. Can you now depict a molecule of water showing the nature of bonding between 1 oxygen and 2 hydrogen atoms? Does the molecule have single bonds or double bonds? What would happen in the case of a diatomic molecule of nitrogen? Nitrogen has the atomic number 7. What would be its electronic configuration and its combining capacity? In order to attain an octet, each nitrogen atom in a molecule of nitrogen contributes 3 electrons, giving rise to 3 shared pairs of electrons. This is said to constitute a triple bond between the 2 atoms. The electron dot structure of N2 and its triple bond can be depicted as in figure 4.4. A molecule of ammonia has the formula NH3. Can you draw the electron dot structure for this molecule showing how all 4 atoms achieve noble gas configuration? Will the molecule have single, double or triple bonds? Let us now take a look at methane, which is a compound of carbon. Methane is widely used as a fuel and is a major component of biogas and compressed natural gas (CNG). It is also one of the simplest compounds formed by carbon. Methane has a formula CH4. Hydrogen, as you know, has the valency of 1. Carbon is a tetravalent because it has 4 valence electrons. In order to achieve noble gas configuration, carbon shares these electrons with 4 atoms of hydrogen as shown in figure 4.5. Such bonds, which are formed by the sharing of an electron pair between 2 atoms, are known as covalent bonds. Covalently bonded molecules are seen to have strong bonds within the molecule, but intermolecular forces are weak. This gives rise to the no melting and boiling points of the compounds, since the electrons are shared between atoms and no charged particles are formed, since covalent compounds are generally poor conductors of electricity. Allotropes of carbon. The element carbon occurs in different forms in nature with widely varying physical properties. Both diamond and graphite are formed by carbon atoms. The difference lies in the manner in which the carbon atoms are bonded to one another. In diamond, each carbon atom is bonded to form other carbon atoms, forming a rigid three-dimensional structure. In graphite, each carbon atom is bonded to 3 other carbon atoms in the same plane, giving a hexagonal array. One of these bonds is a double bond, and thus the valency of carbon is satisfied. Graphite structure is formed by the hexagonal arrays being placed in layers, one above another. These two different structures result in diamond and graphite having very different physical properties, even though their chemical properties are the same. Diamond is the hardest substance known, while graphite is smooth and slippery. Graphite is also a very good conductor of electricity, unlike other non-metals that you studied in the previous chapter. Diamonds can be synthesized by subjecting pure carbon to very high pressure and temperature. These synthetic diamonds are small but are otherwise indistinguishable from natural diamonds. Fullerenes form another class of carbon allotropes. The first one to be identified was C60, which has carbon atoms arranged in the shape of a football. Since this looked like the geodesic dome designed by the US architect Buckminster Fuller, the molecule was named fullerene. Questions. There are 2 questions. First, what would be the electron dot structure of carbon dioxide, which has the formula CO2? Second, what would be the electron dot structure of a molecule of sulfur, which is made up of 8 atoms of sulfur? Topic 4.2, Versatile nature of carbon. We have seen the formation of covalent bonds by the sharing of electrons in various elements and compounds. We have also seen the structure of a simple carbon atom, methane. In the beginning of the chapter, we saw how many things we use contain carbon. In fact, we ourselves are made up of carbon compounds. The numbers of carbon compounds whose formulae are known to chemists were recently estimated to be in millions. This outnumbers by a large margin the compounds formed by all the other elements put together. Why is it that this property is seen in carbon and no other element? The nature of the covalent bond enables carbon to form a large number of compounds. 2 factors noticed in the case of carbon are: first, carbon has the unique ability to form bonds with other atoms of carbon, giving rise to large molecules. This property is called catenation. Let me repeat that. Carbon has the unique ability to form bonds with other atoms of carbon, giving rise to large molecules, and this is called catenation. These compounds may have long chains of carbons, branched chains of carbons, or even carbon atoms arranged in rings. In addition, carbon atoms may be linked by a single, double, or triple bonds. Compounds of carbon which are linked by only single bonds between the carbon atoms are called saturated bonds. Compounds of carbon having double or triple bonds between their carbon atoms are called unsaturated bonds. No other element exhibits the property of catenation to the extent seen in carbon compounds. Silicon forms compounds with hydrogen which have chains of up to 7 or 8 atoms, but these compounds are very reactive. The carbon-carbon bond is very strong and hence stable. This gives us the large number of compounds with many carbon atoms linked to each other. Second, since carbon has a valency of 4, it is capable of bonding with 4 other atoms of carbon or atoms of some other monovalent element. Compounds of carbon are formed with oxygen, hydrogen, nitrogen, sulfur, chlorine and many other elements, giving rise to compounds with specific properties which depend on the elements other than carbon present in the molecule. Again, the bonds that carbon forms with most other elements are very strong, making these compounds exceptionally stable. One reason for the formation of strong bonds by carbon is its small size. This enables the nucleus to hold on to the shared pairs of electrons strongly. Let me repeat that. One reason for the formation of strong bonds by carbon is its small size, as this enables the nucleus to hold on to the shared pairs of electrons strongly. The bonds formed by elements having bigger atoms are much weaker. Organic compounds. The two characteristic features seen in carbon, that is tetravalency and catenation, put together give rise to large number of compounds. Many have the same non-carbon atom or group of atoms attached to different carbon chains. These compounds were initially extracted from natural substances, and it was thought that these carbon compounds or organic compounds could only be formed within a living system. That is, it was postulated that a vital force was necessary for their synthesis. Friedrich Wöhler, excuse my pronunciation, disapproved this in 1828 by preparing urea from ammonium cyanate. But carbon compounds, except for carbides, oxides of carbon, carbonate and hydrogen carbonate salts, continue to be studied under organic chemistry. Saturated and unsaturated carbon compounds. Topic 4.2.1. We have already seen the structure of methane. Another compound formed between carbon and hydrogen is ethane with the formula C2H6. In order to arrive at the structure of simple carbon compounds, the first step is to link the carbon atoms together with a single bond. Then, use the hydrogen atoms to satisfy the remaining valencies of the carbon. For example, the structure of ethane is arrived in the following steps. C, single bond, C. 3 valencies of each carbon atoms remain unsatisfied, so each is bonded with 3 hydrogen atoms, giving this diagram. The electron dot structure of ethane is shown in figure 4.6. Can you draw the structure of propane, which has the molecular formula C3H8 in the similar manner? You will see that valencies of all the atoms are satisfied by single bonds between them. Such carbon compounds are called saturated compounds. The compounds which have single bond are called saturated compounds. These compounds are normally not very reactive. However, another compound of carbon and hydrogen has the formula C2H4 and is called ethane. How can this molecule be depicted? We follow the same stepwise approach as above. We see that 1 valency per carbon atoms remain unsatisfied. This can be satisfied only if there is double bond between the 2 carbons. The electron dot structure for ethane is given in figure 4.7. Yet another compound of hydrogen and carbon has the formula C2H2 and is called ethyne. Can you draw the electron dot structure for ethyne? how many bonds are necessary between the two carbon atoms in order to satisfy their valencies. Such compounds of carbon having double or triple bonds between them are known as unsaturated carbon compounds, and they are more reactive than the saturated carbon compounds. Topic 4.2.2 Chains, branches and rings. In the earlier section, we mentioned the carbon compounds methane, ethane and propane containing respectively 1, 2 and 3 carbon atoms. Such chains of carbon atoms can contain many more carbon atoms. The names and structure of 6 of these are given in table 4.2. First, methane, formula CH4. Second, ethane, formula C2H6. Third, propane, formula C3H8. Fourth, butane, formula C4H10. Fifth, pentane, formula C5H12. Sixth, hexane, formula C6H14. Notice that all of this end with ane suffix. Now this suffix is important as this represents a single bond. You will see about it later on. But let us take another look at butane. If we make the carbon skeleton with 4 carbon atoms, we see that 2 different possible skeletons are. Filling the remaining valencies with hydrogen give us. We see that both of these structures have the same formula C4H10. Such compounds are identical molecular formula but different structures are called structural isomers. Different formula but same structure are called structural isomers. In addition to straight and branched carbon chains, some compounds have carbon atoms arranged in the form of a ring. This example, cyclohexane, has the formula C6H12 in the following structure. Can you draw the electron dot structure for cyclohexane? Straight chain, branch chain and cyclic carbon compounds all may be unsaturated or saturated. For example, benzene, C6H6, which has the following structure. All these carbon compounds which contain only carbon and hydrogen are called hydrocarbons. Compounds which contain carbon and hydrogen are hydrocarbons. Among these, the saturated hydrocarbons are called alkanes. So now the compound which have hydrogen and carbons and which are saturated, which means which have only single bonds in them, are called alkanes. A-L-K-A-N-E-S. The spelling is important. The unsaturated hydrocarbons which contain one or more double bonds are called alkenes. A-L-K-E-N-E-S. The unsaturated hydrocarbons which contain one or more double bonds are called alkenes, and the one which contains saturated hydrocarbons are called alkanes. Those containing one or more triple bonds are called alkynes. Topic 4.2.3 Will you be my friend? Carbon seems to be a very friendly element. So far we have been looking at the compounds containing carbon and hydrogen only, but carbon also forms bonds with other elements such as halogens, oxygen, nitrogen and sulfur. In a hydrocarbon chain, one or more hydrogens can be replaced by these elements. So one or more hydrogens can be replaced by oxygen, nitrogen or sulfur such that the valency of carbon remains satisfied. In such compounds, the element replacing hydrogen is referred to as heteroatom. The element replacing the hydrogen is referred to as heteroatom. These heteroatoms are also present in some groups as given in table 4.3. These heteroatoms and the group containing this confer specific properties to the compound regardless of the length and nature of carbon chain, and hence are called functional groups. The group containing these confer specific properties to the compound regardless of the length and nature of carbon chain and hence are called functional groups. Some important functional groups are given in table 4.3. Free valency or valencies of the group are shown by single line. The functional group is attached to the carbon chain through the valency by replacing one hydrogen atom or atoms. Heteroatom. Chlorine/bromine. Class of compounds. Halo compounds. Chloro-bromo-alkane. Formula of functional group. Free valency single bond chlorine or free valency single bond bromine. Heteroatom oxygen. Class of compounds. First, alcohol. Free valency single bond OH. Second, aldehyde. Free valency single bond carbon, single bond hydrogen, carbon double bond oxygen. Third, ketone. Free valency carbon double bond oxygen, carbon single bond free valency. Fourth, carboxylic acid. Free valency carbon double bond oxygen, carbon single bond OH. Topic 4.2.4 Homologous series. You have seen that carbon atoms can be linked together to form chains of varying lengths. These chains can be branched also. In addition, hydrogen atom or other atoms on these carbon chains can be replaced by any of the functional groups that we saw above. The presence of a functional group such as alcohol decides the properties of the carbon compound regardless of the length of the carbon chain. For example, the chemical properties of CH3OH, C2H5OH, C3H7OH and C4H9OH are all very similar. Hence, such a series of compounds in which the same functional group substitutes for hydrogen in a carbon chain is called homologous series. Let us look at the homologous series that we saw earlier in table 4.2. If we look at the formulae of successive compounds, say CH4 and C2H6, they differ by a single bond CH2 unit. C2H6 and C3H8, these differ by a single bond CH2 unit. What is the difference between the next pair, propane and butane? Can you find out the difference in molecular masses between these pairs? The atomic mass of a carbon is 12 AMU and the atomic mass of hydrogen is 1 AMU. Similarly, take the homologous series for alkenes. The first member of the series is ethane, which we have already came across in section 4.2.1. What is the formula for ethane? The succeeding members have the formula C3H6, C4H8 and C5H10. Do these also differ by a single bond CH2 unit? Do you see any relation between the number of carbon and hydrogen atom in these compounds? The general formula for alkenes can be written as CnH2n, where n can be any number. Can you simply generate the general formula for alkanes and alkynes? As the molecular mass increases in any homologous series, a gradation in physical properties is seen. This is because the melting and boiling points increase with increasing molecular mass. Other physical properties such as solubility in a particular solvent also shows a similar gradation, but the chemical properties which are determined solely by the functional group remain similar in a homologous series. Activity 4.2. Calculate the difference in the formula and molecular masses for A, CH3OH and C2H5OH, B, C2H5OH and C3H7OH, C, C3H7OH and C4H9OH. Is there any similarity in 3? Arrange these alcohols in the order of increasing carbon atoms to get a family. Can we call this family a homologous series? Generate the homologous series for compounds containing up to 4 carbons for the other functional groups given in table 4.3.